Hi everyone, welcome to another video in my channel. My name is Luis Gregorio Diaz, and today I'm going to discuss the possible retraction of this paper, the Quantized Majorana conductance paper by Leo Kuijnhoven's group and other collaborators that was published in Nature in April of 2018. This is a topic that we discussed in our group meeting here at the University of São Paulo. And I decided to record this video because it might be of interest to other people as well, and I'll give you my personal take on this. Let me say I'm not involved in this work. I'm just a curious observer, but there are some lessons here that we could learn. So let me just make the point that this is not a introductory video. It does not tell the story of Majorana peaks in transport experiments from the beginning. There are other sources that you can go to if you want to learn more about where these Majorana bound states are and so on and so forth. I might record a more basic video on this, but this is a video more to specialists, to people who are following the field. I'll give you some hints of what's going on, but this is not for a general audience that doesn't know what these Majorana bound states are. All right, so let's go right into it. All right, so let's start by first stating the title of both papers. I mean, this is the original Nature paper that I mentioned. And this is a paper that was published in the arXiv at the end of January 2021 from the same group. It's not the same authors actually involved, but pretty much the same group. And in the comments for this arXiv paper, it said that this manuscript replaces the Quantized Majorana conductance Nature paper. They say technical errors in that paper are corrected, and the original claims now have a wider interpretation. A retraction note, which is in preparation, will include a detailed description of the errors and the corrected data analysis. Okay, first let's notice that here the peak, or rather the title of the retraction paper, let's call it the retraction paper, does not mention Majoranas. It says large zero bias peaks in indium antimonide aluminum hybrid semiconductors, superconductor nanowire devices. So, it's a toned down from the original Quantized Majorana conductance. And let's take a look why this paper, Quantized Majorana conductance, why was the claim so strong? Why was it published in Nature and so on? So let's take a look at the abstract of this paper. So this is the abstract of the Nature paper, and it tells us about Majorana zero modes. As I mentioned in the introduction, I'm not going to go over what these Majorana zero modes are. I might record a video later, but it says a type of localized quasi-particle holds great promise for topological quantum computing, and that's why everybody is interested in this practice, and why Microsoft itself is involved in there too. And the tunneling spectroscopy in electric transport is a primary tool for identifying the presence of Majorana zero modes. That's one of the first experiments in Majoranas in this sense was from the Delft group, Leo Kuijnhoven's group, where they did see a signature in transport experiments for these Majorana zero modes. However, the height of the zero bias peaks in theory should be quantized at 2e squared over h. And in those earlier experiments, these zero bias peaks were not nearly close to that. It was much smaller, and there were some, better samples and so on with this. So they had a peak. It was within the range of parameters where it should be, but never reached 2e squared over h. So that was one among many other criticisms of why, you might not expect this to be Majorana, it's not perfect conductance, so on and so forth. Let me tell you that there are many other mechanisms that could lead to quantized conductance. For instance, perfect transmission through a resonant level could lead you to that. The other is transfer through a condo-like peak coming from condo effect, is something that I'm more familiar with, could give you also 2e square over h. So getting a 2e square over h conductance through a Majorana peak, is a good sign, but by no means a as they call it, a smoking gun signature. But in any way, in the paper they report a quantized conductance, plateau, zero bias. So it would be nice if this were consistent. I mean, it gives you a plateau. So, and they say that we distinguish these quantized Majorana peaks from possible non-Majorana origins by investigating its robustness to electric and magnetic fields, as well as temperature dependence. So, that there was the claim over the original paper. We're seeing this quantized Majorana conductance. We see the peaks where the theory tells us that it should be. And this is, for instance, a sample of the results of the first paper. Here's the device. You have the nanowire with this coating of aluminum, which is a superconductor. So you have a nanowire with strong spin orbit, and in proximity with a superconductor, so it induces superconductivity into the electrons in the wire by proximity. I'm not going to go into details of that, but that, along with the magnetic field, would give you the ingredients for producing Majorana bound states at the ends of the wire. And they see these peaks where they and you have these zero bias peaks where they should, they're pretty much the right value of magnetic field, so on and so forth. And they compare that with the theory, and they get a peak with a height of 2e squared over h. Right, so that's promising here. Theory also gives you the same, right? So you have the merging of these bands, and then here at zero bias you see this nice peak, this Majorana peaks, with a plateau of conductance of 2e squared over h. And that matches the experiment, so this, everybody's happy with this, right? So this plateau coming here. All right, so that was 2018. Let me give you another interesting point here. This is a function of magnetic field, okay? But they also do these experiments as a function of this tunnel gate voltage, which in essence essentially opens up or closes down, narrows the barrier between the leads and the wires. So essentially, it can be another measure for you to see this conductance, and that's what they do here. These are all for minus 7.7 volts, and they vary this, keeping the magnetic field at 0.8. So let's go back one more, 0.8. So you're a minus 0.77. You are here, right? 0.8 minus 0.77. You are here, and now we start changing this. So once you change this, for at some point you lose the plateau, but this data shows that here, once you reach this point, minus 7.95, something like that, you start getting this plateau, and it stays there. And you calculate with the theory, and everything seems to work, right? So these peaks, they are at most height 2e squared over h. Here is not perfectly because you don't have the Majoranas still there. But at the end of the day, you have this height at 2e squared over h, very consistent, and all these curves, they tend to approach 2e squared over h here for EC 0.8, and this is at zero bias. Now this is a function of bias. All right, so okay, look at this data, say, wow, that's impressive. Now, let's go to the retraction paper and where they revisit these results, okay? So this is the January paper in the arXiv, where they state the following, right? So they say, this is right at the introduction. The majority of the experimental papers have reported zero bias peaks, much lower than 2e squared over h. Tunnelist spectroscopy on nanowires defined in a 2D electron gas was shown the heights near 2e squared over h, which is very similar to the abstract of the original Nature paper, if you look. Now, we reported this as an observation of conductance quantization served as evidence for Majorana-bound states, and after several issues were brought to our attention, we re-examined the data and as well as the technical details of our experimental setup. During this process, discrepancies with the original publication arose, which led us to conclude that we can no longer claim robust quantization, leading to a full retraction of the paper. Wow. So this is, they're saying that, they revisited their data and the technical details, and they threw out the main conclusion for that Nature paper. And they say, our work presented here, along with recent theoretical developments involve quasi-Majoranas and disorder, I'll mention that at the end of the talk, at the end of the video, should serve as strong cautionary message for all Majorana experiments in all platforms. This is strong. And they still say, clear emphasizing that experimental observation of zero bias conductance peaks, no matter how compelling, should be considered only as necessary and by no means sufficient conditions for the existence of topological Majorana zero modes. So what they're saying is that all the other experiments that have been out there from several groups, not only them, but all as well as the group in Copenhagen and others, should be taken with a grain of salt. All right, so it's quite strong words here, right? All Majorana experiments in all platforms. They're saying, okay, even if you get a nice zero bias peak with perfect conductance at the right parameters, that cannot tell you that these are indeed Majoranas, right? And to be sure, this has been pointed out by others as well, saying that the only way to unambiguously prove that you were actually observing Majorana-bound states is to do some sort of braiding experiment, which is of course much harder. But let's now take a look at the data they present in this retraction paper. Okay, so now we're comparing figure 2 from the original Nature paper and figure 3 in this arXiv retraction paper, which should show the same thing, but here there's additional data. Notice that here in the original paper, there's of course all these sections here. There's vertical kind of lines, and they seem to show that there's some sort of small jumps in the data, especially here at high bias, right? It's around 0.2, and that's showing in these curves where they plot the conductance precisely at 0.2 and minus 0.2, and you see this little steps here, and it's expected that at finite bias you should have some features in the conductance. Essentially, the transmission through the device now will be happening through excited state, so you might have, say crossings in a spectrum, and that will lead to the jumps. And the point of this figure is that in spite of these jumps at large bias, there should be a plateau here at zero bias, and that's the point of them showing this data for large and slow bias. Now, in the retraction paper, they do show some extra data with some interesting features. For instance, here, right at this point where you have around -8, this is the top gate voltage, right? So this is a function of this top gate voltage or tunnel gate voltage here, right? Remember, this was -7.7. And here you do see a big jump even at zero bias, right? You see a jump here at large bias, but you see a big jump here. And they refer this, and this is absent from the original paper, right? This big dip in conductance here. And now they attribute that to charge jumps. Essentially, it could come from disorder or something, right? But it's affecting the zero bias peak, and it's by no means something that you can notice. I mean, it's right there in the color plot of the data. So yeah, you do have something happening at large bias, 0.2 minus 0.2, a jump here, but you have a correlated jump here at zero bias. So this here might not be topological after all, right? And you do see some things happening here too, right? This green is what I call the above gate conductance, which is essentially an average of the conductance for large values of bias in absolute value, right? So this is the green. So this is essentially telling you what's going on at higher energies, right? So not at zero bias. Okay, and whenever you see a jump in this, you look for a correlation of what's going on here, you might be, if this is not consistently 1, even when you have these jumps, then that they do have to revisit their data, or rather their results. But the point is, okay, this increases a lot with top gate. So this is essentially a proxy for the transmission, the single particle transmission through the device, while this remains mostly constant, but by no means around 1. And notice that they also added here this other data after this jumps in the above gap conductance, where now there's clearly a decline in the zero bias conductance. So this tells a much different story than this figure. Well, not a much different story, but definitely there are details here that were not included here. In particular, the fact that here for these values of tunnel gate voltage, this figure shows the data oscillating around 1 pretty much, while here it deviates from 1 much more than what is shown here. Like this little bump here is right at 1, here is clearly above 1, and this deviation can go all the way to, I don't know, what's that, 0.4, this might be 20%. Okay, so you get this point here, very close to 1, this is 20% above. So it's not so easy to disconsider these oscillations. Anyway, this plot here tells a slightly different story, or maybe a different story than this one, that's for sure. And let me tell you that these features in the data have been noticed by other people, in particular Professor Sergei Frolov at the University of Pittsburgh, who was also a co-author in the original 2012 paper out of the Delft group. And he noticed these charge jumps and this absence in the data, that this and this part were not included in the original figure of the Nature paper. And also Vincent Mulrich, who was the first author in the 2012 paper, And even now in the retraction paper, they say that the Delft group say that charge jumps, what they call charge jumps like that. So this might come from additional charges that are in the sample. Essentially, you can consider this disorder, charge disorder, if you wish. And this is, they say that's common in their data. So yeah, they also pointed out this in Twitter, actually, his Twitter account, and it's surprising how much of this discussion is going on at Twitter, and I'll give you another example of this a little bit later. Okay, so another example. This is the conductance as a function of bias voltage for a given valid magnetic field. So it's just essentially a cross section of the data in the previous figure. This is from figure 2 in the original paper, and this is figure 4. So here, as we mentioned, they say that after a certain value of the tunnel gate voltage, it goes to a plateau, and this tells a much different story. So that data point there that goes all the way to 20% above, there's a curve behind it that shows a different story. And one point that they're going to talk, and this illustrates quite nicely here, is that that charge, that above gap conductance that they mentioned, is essentially the average of these curves, or this plateau value here above 0.2. So they call that, they try to do a correlation between the value here and the peak height there. So whenever you might increase this, right? You might increase this, but the peak value stays. So that's one of the points they say, okay, this is consistency in your data. And here, this correlation is not so clear. I mean, this is increasing, and this might be increasing as well, or at least fluctuating, not by the same amount or the same ratio if you want, but still. So let's take a closer look on this. So this is what I'm talking about. So here they plot the height of the peak as a function of that above gap conductance, right? So if we go back one, this is 0.5, so this above gap conductance is slightly below 0.5, right? So it's in this range here. So that's what they're plotting. So it goes from, say, 0.42 to 0.5, and here they say that the height stays around 1, right? Whenever this above gap conductance is around 0.5, not only the height stays above 1, but the peak, the width of the peak in this peak here, right? This width in bias voltage also increases. Okay, so then, but I think the most telling thing is here in the height. Okay, so the height stays around 2e squared over h, while you have an increase in the above gap conductance. Now, the additional data in the arXiv paper tells a much different story, right? So, okay, you do have an increase in the above gap conductance, but you have a fluctuation in sometimes increase, sometimes a decrease, but you have a fluctuation in the height that you cannot say that this stays at 1. That's for sure, right? And it's good that they came out with this, they came clean with this extra data here, because it tells a very different story from what we have here. So you have 0.35 to 0.55, and tells the story of this plot, right? So you might have a situation where you are in this range here in above gap conductance, and you have an height 20% above 1.2. something like this, right? And yeah, so that's what's going on here. And therefore you cannot make the claim of the quantized plateau anymore. Definitely this and this are different things. Notice that the error bars here. Clearly these points are way above 1 outside their error bar. And yeah. So this video is already getting a little bit too long, but let me go right into the conclusions or the discussions in the retraction paper. So what I say is that we note, however, that these plateaus are the results of a dedicated search motivated by plateaus, that such plateau behavior would be the indicative for MZMs. All right, so yeah, they went into this looking for something, right? They were looking for these plateaus. And they say, although for local spectroscopy experiments, we cannot think of another method such as dedicated search has a potential to lead to confirmation bias and effectively yield false positive evidence of MZMs. So I think the key word here is confirmation bias. So if you go into something looking to find it, well, you will tend to trust the portions of your data that tells you the story that you were already set to find it true, than the points that do not agree with your narrative. And that's, you know, known for many different contexts, that is a cognitive bias that we all have, this confirmation bias. Social network, we tend to believe that, you know, that information that we receive that agrees with what we think, but that's very dangerous for science. So it's good that they did this, actually posted this extra paper, and they are discussing this, right? Or data sets or any other data set report in literature that we know of can make a distinction between the different possible origins dubbed as the good, the bad, and the ugly. And let me discuss this a little bit because it's important. And it talks about disorder, right? So that term, the good, the bad, and the ugly, is of course from a title from a Western, this so-called spaghetti Western from Sergio Leone with Clint Eastwood. If you haven't watched it, you should. It's a classic. But it's also mentioned here in this paper by Professor Shankar Das Sarma and his PhD student Henning Pan, where they talk about these physical mechanisms for zero bias conductance peaks in Majorana nanowires. And they discuss the good with no disorder, the bad, a little bit of disorder, and ugly, strong disorder, right? So, and they mention that they present results for the good and bad scenarios for zero bias peaks. They mention that they argue, at least, that ugly zero bias conductance peaks around from strong disorder can be present in the experiments, and they even go out and say that all experimentally observed zero bias peaks in Majorana nanowires are most likely ugly, purely induced by strong disorder. So this is behind the scenes. And let me mention that Professor Das Sarma is also a co-author in both the 2018 Nature paper and in the Retraction paper from this year. So they are saying essentially that disorder might be playing a role here. So the answer would be to have cleaner samples. And even more, they published this figure on their Twitter account, the Condensed Matter Theory Center at University of Maryland, where they do a simulation using disorder that, in a sense, matches some of the results present in the retraction paper, right? So you have these peaks here, with nice unitary conductance, but you also have, depending on the barrier height. I didn't look at, or at least I didn't find this figure in the paper, but it should be coming out soon. But I think here what they're doing is they changing the barrier height, which might depend, of course, on disorder, and they do get different conductance maximums for the different cases. So it'll be interesting to take a look at this paper, but it definitely matches what they show in the arXiv retraction paper. Okay, to wrap up, here are some quick questions and my own answer, my own opinions, right? So in light of all that we have seen, should the 2018 Nature paper be withdrawn? I think that the answer is definitely yes. There's strong evidence in the data that the data does not back the main conclusions of that paper. Now, was there any scientific misconduct involved there? I think probably not. Most likely not. I think they did a honest work in terms of, doing the experiments and putting their data to their best knowledge that was solid data. They did, however, suppress some of the data that were not according to the conclusions. So did confirmation bias play a role there? That's most likely yes. So is that point where you selective decide for cosmetic reasons, or maybe even say, okay, oh no, this data point is not consistent, maybe you should redo the experiment and so on. But that leads to confirmation bias, which is dangerous. And you have to commend them by having the courage of putting their data out, even though there'll be a lot of criticism and how this was handled. But honestly, I think it takes courage to do retraction of a paper of that magnitude. So is the pressure to publish outstanding results in a high-impact journal such as Nature's part of the problem? I think yes. So there's a lot of pressure involved. Maybe you have to work, you have to, take shortcuts in the data analysis. You might not have time to process the data in a way that it should. There's pressures from different sources. There's funding, there's competition, and so on. So I think this was part of what went on here. So did the scientific process work in this case? I think yes. So they did. They put out the paper. There was criticism. People looked at the original data and they start asking questions. And the authors themselves had their critique of their own work. So that, I think that's the scientific process at work here, as it should, right? Now, is it game over? Can one rule out that the part of the signal comes from Majorana bound states? I think no. I think maybe there's still Majoranas there. You just cannot tell them with it with this experiment. I mean, maybe if you have samples with lower disorder, that will show better signals. But with this type of experiments for single transport spectroscopy, is really hard to pinpoint that, to answer that from 100%. So, and can we still find and confirm the presence of Majorana bound states? I think yes, in cleaner samples, different platforms, and I'll present on my own group. We're looking for different ways of having these Majoranas in platforms involving 2D materials such as silicon or other materials, which can be make in samples which are much cleaner than those nanowires. So I think that opens many opportunities for other platforms that may become competitive now. And of course, other kinds of experiments such that can involve braiding, for instance. So at the end, I think this is bad news in a sense, but also opens a whole host of possibilities for looking at different platforms and improve the quality of the samples. Okay, so I hope you enjoyed the video, and I'll see you next time.